All right, in the previous video, we learned about the physics behind a hydraulic jump. And here what we would like to do is to find out a relationship for h2, the height after the hydraulic jump, to h1, the height of the water before the hydraulic jump, as a function of other variables involved. All right, so here's the way we're going to proceed. Let me draw again the schematic here. So this is the schematic, and then we have a stream basically flowing over this rigid surface, and at some point we're going to have a hydraulic jump, right, with a lot of turbulence and everything here, and then it's going to basically result in another relatively uniform stream, right? So what we're interested in is what happens in this area before the hydraulic jump to after the hydraulic jump. And maybe I go a little further. All right here. This is the region of interest. So we're interested in h1 over h2. So following the systematic procedure, important or relevant, let's just put it relevant variables or quantities are, of course, we're looking for h1, the height before the jump, h1, and h2, the height after the jump. And then because it's a free surface flow, gravity or gravitational acceleration is important. The velocity v1 is important. And I believe that's it. The reason, because the control volume or the area that we're interested in is a pretty small area, then the effect of viscosity can be neglected to the leading order. Again, viscosity plays a very important role for the development of the hydraulic jump. But again, going from h1 to h2 in this tiny area, we just assume that viscosity doesn't play a major role. All right. So the standard procedure is to go with the dimension table. All right, so I'm gonna basically quickly draw. See, yeah, there you go. And actually, we need to have three. So let's just get rid of this here. Okay, right there. All right, and then the quantity is m, l, and t, the dimensions. And then we have the variables, our variables, they are h1, h2, g, and v. All right, so filling the table, what we're going to have is h is just 1, 0, h2 is 1, 0, g is 0, 1, negative 2, and velocity is 1, negative 1. Now, the rank of this matrix, so first of all, the number of variables n is equal to 4. The rank of this matrix R, H1 and H2, of course, are dependent, right? One column can be derived from the other column. And then we don't have mass in either of these, so we can conclude that the rank of this matrix is 2. Now, as I said, you may just ask a calculator or type it in a software programming language and quickly calculate the R or the rank of this matrix for you. But definitely the rank of this matrix is less than 3, less than or equal to 3, because this is a 3 by 4 matrix, and then it turns out to be 2 because we don't have any mass. And again, this is kind of a it may be a good argument, but again, just do it yourself, just to convince yourself that that's the case. So therefore, from Buckingham pi theorem, we conclude that the number of dimensionless variables are n minus r, so that's 4 minus 2, so we're going to have 2 independent dimensionless groups. Now we have to pick the core variables. All right, so as for the core variables, I'm going to pick core variables. I'm going to pick h1 and g. and that's it. I need 2 core variables, so that's good enough. So now let's see. So pi 1 therefore is going to be h1 to the power alpha g to the power beta times the first variable that we've not picked from the 4 variables. So let's say h2. That is, well, this is a dimensionless group. So now talking about the dimension of the system, h1 as a dimension of length to the power alpha, g is lt squared to the power beta, and h2 has l. So that is l to the power alpha plus beta plus 1, and t to the power negative 2 beta, and this has to be equal to 1. So therefore, we conclude that alpha plus beta plus 1 has to be equal to 0, and negative 2 beta is equal to 0. So from here, beta is equal to 0, and from here we conclude that alpha is equal to negative 1. So therefore, our pi 1 is going to be h1 to the power negative 1, a g to the power 0, and h2. So this is h2 over h1. All right. So pi 1 is h2 over h1. And this is our first important result here. The box about it. There you go. All right. Now let's go to the second pi. Pi 2 is equal to h1 to the power alpha g to the power beta times velocity, and that is L to the power alpha, L over t squared to the power beta, and L over t, that has to be equal to 1. And let me just continue here. So that's going to be L to the power alpha plus beta plus 1 times t to the power negative 2 beta minus 1. This has to be equal to 1. Therefore, we conclude that alpha plus beta plus 1 has to be 0. Negative 2 beta minus 1 is equal to 0. From here, beta is equal to negative 1/2. And then from here, alpha is going to be equal to negative 1/2 as well. So therefore, pi 2 is h1 to the power negative 1/2, g to the power negative 1/2, and v. All right, and velocity is the input velocity. Or in other words, pi 2 is going to be g over the square root of gh. And that's going to be our second dimensionless group. All right, so therefore, from Buckingham pi theorem, the final solution to this problem is f of h2 over h1 and v, and this is the input velocity, so I put v1 over the square root of gh1, and remember this is h1 also here, and these are all h1. All right, that is equal to 0, or I can just solve this equation for h2 plus h1. So I get h2 over h1 is a function of v1 over square root of gh1. This is the equation that we wanted to get. All right, just Control C. All right, there you go. So we found a relationship for h2 over h1 as a function of other quantities involved, and it looks like there's just one dimensionless group that we are interested in, and that is v1 over square root of gh1. Now there's an important physics associated with this v1 over gh1 that I'm going to talk about in the next video.